SN9 is factoring and solving polynomials. So in 9.1, we're going to factor, in 9.2, we're going to solve. We're just going to build off what we already know about factoring and then learn a couple new patterns that will come into play during this unit. So 9.1, our first new pattern is the difference of cubes. So remember, difference means subtraction, and then cubes is referring to perfect cubes, kind of like how there's perfect squares. Those are like the numbers that you can take the square root of. So like 1, 4, 9, 16, and so on. There's also perfect cubes. We get these numbers by taking other numbers and raising them to the third power. So for example, like 1 is a perfect cube because it's 1 to the third power. And like 8 is a perfect cube because it's because it's 2 to the third power, or 2 cubed, which just means 2 times 2 times 2. And then so on, like 3 cubed is 27, 4 cubed is 64. So all the ones on the right side of this like upper right table, the ones that are highlighted in yellow, those are perfect cubes. So those are numbers that we would look for when we were trying to use this pattern. So the pattern itself is a cubed minus b cubed. It factors into a minus b times a squared plus ab plus b squared. We're going to have numbers in there when we write our final answer, some variables, some numbers, as opposed to just a's and b's. So the first step is to take the problem that you're given. So we're given x cubed minus 8, and I want to rewrite it so it looks as much like this a cubed minus b cubed as possible. So one number to the third power minus another. So I know that 8 is 2 to the third power, so I'm just going to rewrite 8 as 2 to the third power. So x to the third power minus 2 to the third power. And then now it looks pretty similar to a cubed minus b cubed, but I do that so I can see, what a is and what b is. A and b are just the base, like they're not the whole thing, they're just the base, the bottom part that's being raised to the third power essentially. So in this case, my a would be x, and then my b would be 2. And a is always first, b is always second in this case. So a is x, b is 2. And then now that we know that, we're ready to go ahead and take both those and plug them into this part of the formula. So we're given the left side of the equal sign, we're trying to get to the right side. So a is x, so I'm going to put x in for all of my a's, and then b is 2, so I'm going to put 2 in for all of my b's, and then simplify. So it'll be a minus b, nope, sorry, I don't know why I wrote a and b again. It is a minus b, that's what we're plugging into, but we have to actually put the numbers in there. So a is x, or numbers and variables, minus b is going to be minus 2, and then parentheses. Now we're on to the second parentheses over here. So first is a squared, so it's going to be x squared, and then plus a times b, so plus x times 2, but we write the number in front, so we would write that as 2x. And then last is this b squared. So since b is 2, it would be plus 2 squared, but we should just go ahead and put it in its simplest form. So 2 squared means 2 times 2, so plus 4 at the end. And then sometimes it looks like this trinomial can be factored more. I haven't seen the case where it can be factored more. I don't think it ever really can, but if you see something where it can, please let me know and prove me wrong. But like if we were to check to see if it was factorable, a is 1, so I would need numbers that multiply to 4 and add up to 2, and those numbers don't exist, so it cannot be factored any further. So our final answer is x minus 2 times x squared plus 2x plus 4. And then our next pattern is the sum of cubes. So it's almost exactly the same. There's a couple signs that are switched. So it's one perfect cube plus another this time because sum means to add. And then the only thing that are different between like the two difference of cubes and sum of cubes is difference of cubes is a minus b. Right there, sum of cubes is a plus b first. And then in the second parentheses, this is a plus ab versus this is a minus ab. So they're very, very similar, just kind of the signs switch on a couple different terms. Okay, so our example is x cubed plus 64 over 343. So you may maybe recognize 64 and 343 from this list up here. So because they're both perfect cubes, even though they're a fraction, we can technically rewrite it as like, just something to the third power. Because when you raise fractions to the third power, they just stay as fractions in that same form. Okay, so the first thing I want to do is I want to rewrite 64 over 343 as like an exponent, or as an exponential with like not an exponential, but something to the third power, sorry. So this is x to the third. And then I want to rewrite 64 over 343 as something to the third. Since that's a fraction, my base is going to be a fraction as well. So 64 is 4 to the third power. So my numerator would be a 4. And then 343 is 7 to the third power. So in my denominator, it would be 7. Okay, and then now that it's rewritten with like a base to the third power, I can see what my a and b are again. So a is going to be just x. B is going to be 4 over 7, 4 sevenths. So A is x, B is 4 sevenths, and then we treat it the same way, 4 sevenths. We treat it the same way as the last problem, where now we just go ahead and take those and put them into this formula. So A is x, so we'll put x right here, and right here, and then B is 4 sevenths, so we'll put 4 sevenths right here, and right here. Okay, so first is A plus B, so that would be x plus 4 sevenths. And then on to the second parentheses, first is an a squared, so it'd be x squared. And then minus a times b, but we usually put like the number in front. So it'd be minus 4 sevenths, and then times x from like a times b. And then last is b squared, so plus 4 sevenths squared. And then this one I am going to go ahead and just kind of leave that there so we can see that step. And then we just want to go ahead and simplify this part. So when you square a fraction, you just square the numerator and square the denominator. Nothing more than that. So the rest of the problem is going to stay the same. I'm just going to copy it down. So x plus 4 sevenths, and then times x squared minus 4 sevenths x. And then 4 sevenths squared, I would square the 4, so it'd become a 16, and then I would square the 49. Oh, no, I would square the 7, and that would become a 49. And then I'll close the parentheses. So this one would be x plus 4 sevenths times x squared minus 4 sevenths x plus 16 over 49. And then that 16 over 49 cannot be reduced or anything like that. Okay, so the next pattern is a pattern you learned in Algebra 1. It's a difference of squares. We're just going to kind of build on it here, so it'll be a little bit more challenging problem than you've probably seen in Algebra 1. So difference of squares, hopefully remember it. If not, it's no big deal. It's one perfect square minus another. Remember, difference means subtraction. So one perfect square minus another, a squared minus b squared factors into a plus b times a minus b. So the first thing I want to do is I want to take my problem and I want to rewrite it as like a base to the second power minus a base to the second power. It kind of looks like that now, but it's almost like deceiving the way it's written right now, especially for like the 36y squared. Okay, so for x to the fourth, to get that to be something like raised to the second power, when you have an exponent raised to another exponent, you multiply them. So I would have to rewrite x to the fourth as x squared squared. I'd want to rewrite it so it's like a base to the second power. And I'm going to rewrite it using the power property for exponents, where if you raise an exponent to another, you multiply them. So between x to the fourth and like the x squared squared, it's the same value. It just now I can see what's being squared to get there. And then the 36y squared is a little bit tricky. So technically, as it's written in the original problem, only the y is being squared because there's no parentheses. So if I wanted to rewrite this as like what quantity was being squared, like all in parentheses, I would have to think, what do I need to square to, sorry, what do I need to square to get to 36? And I would have to square 6. So like this would be a 6y inside here. Because this means like, all of 6y is being squared. So like the 6 would become a 36 and the y would become a y squared. Okay, so now we can see what a and b are. So a is x squared, b is just 6y, not negative or anything like that. The minus is in the formula, so we don't have to worry about negatives here. So a is x squared, b is 6y. We're going to take that and put it into this a plus b times a minus b. I'm going to have to probably go into like two different columns just space-wise. So I'm going to start writing over here. So first will be my a plus b. Actually, no, I won't have to go into two columns. I'll go straight down. I think I was getting ahead of myself. So first is going to be my a plus b. So that's x squared plus 6y. And then a minus b is x squared minus 6y. Okay, so this is my a, and then plus b, and then a minus b over here. And it doesn't matter like which factor you put first. Like if you did a minus first, that's okay. When you have kind of like higher powers here, you just really want to be careful to make sure that like you can't factor it any further. So for example, like over here, if I had like that 6y term was a perfect square, because it's x squared minus that, I could technically factor it further, but like 6y is not a perfect square, so I can't, but it's just something you always want to check for because those problems do kind of pop up a lot. So x squared plus 6y times x squared minus 6y, or you could switch the order and do x squared minus 6y first. Okay, so the next and the last pattern is the perfect square trinomial pattern. So we see it sometimes, or we see it most often when we're completing the square, like we're creating perfect square trinomials, but there is a pattern that you can factor with it. I personally don't like using this pattern, so I'm going to show you two different ways that you can approach this. I'll show you with the pattern and I'll show you without it. Okay, so perfect square trinomial has a squared plus 2ab plus or minus 2ab, and then plus b squared, and then whatever this sign is matches whatever it factors into sign. So if like it's a plus, it'd be a plus on the right side. If it's a minus, it'd be a minus. So in order to see if it fits into that pattern, we'll rewrite. So let me erase some of this. So the first term, 9x to the fourth, is like in the spot of my a squared. So I want to rewrite that as a quantity that is being squared. So something in parentheses squared. And then the like thing that's being squared, to simplify to 9x to the fourth, would have to be a 3x squared. Let me write that a little bit smaller. So the quantity that is being squared to make it equal 9x to the fourth is 3x squared. And then I kind of like to skip the middle term and just go to the last term first. So like plus b squared over here is this like 25. So we can see that, okay, b is 5 because 25 is 5 squared. And then this middle term is supposed to be like 2 times a times b. So we'll just go ahead, like we can see what a and b are now. Like a is 3x squared and then b is 5. So I just want to go ahead and I'm just going to write those as 2 times a times b and see if it like matches up with the original problem, because it's not always the case. So it'll be a plus 2 and then times a, so that was 3x squared, and then times b, which was 5. And then I just want to make sure that what I just wrote here is the same value as 30x squared. So 2 times 3 is 6 times 5 is 30x squared. So it has to be like that exact pattern to be able to like factor this way. And sometimes I feel like checking to see if it falls into that pattern, depending on how complex the numbers are, just takes longer than factoring it the alternative way. Okay, so this is my A, and then B was last, and then this is 2A, B right here. So now that we have those, we know, okay, A is 3x squared, B is 5, and then it says it just factors into A plus B squared. This was a plus, so ours will be a plus also. So now I can just write it as a binomial squared, and then it's A first, so 3x squared, and then plus B, so plus 5. So 3x squared plus 5 squared, and then same thing here, you would always want to check to see like if it could be factored further, like if you had a difference of squares inside the parentheses, then it could be. Okay, so that is one way to factor this problem, but like I said, I'm not a huge fan of that way, so I'm just going to show you the alternative way in case it ever comes in handy for you. So the other way is just to like factor it as you would like any other trinomial. So let's see. So I don't have a GCF I can pull out, and A is not 1, so I have to take A and C and multiply them together. So it would be 9 times 25. It's 225. So 9 times 25 is 225, so I need numbers that multiply to 225 but add up to B, which is 30. So multiply to 225, add up to B, which is 30. Oop, I don't know why I wrote 9. Add up to B, which is 30. And like it may just take like listing a few factors to check it. And it kind of takes time. They both take time. So it's really up to you. I just wanted to show you like both methods so you can decide what you like more. Okay, so I don't know the factors of 225 off the top of my head, so I'm just gonna go ahead and list some until I get to the point where I get a sum of 30. So I did 225 divided by 5, that was 45. So 5 and 45, that doesn't add up to 30. So we could do 225 divided by 15. That's 15, so I get 15 and 15. Like, okay, that adds up to 30. So those must be my two numbers. So then we kind of go back to like the same process we use when we're factoring like regular trinomials. So we take that like value, and that's how we break down our 30x squared, like our middle term. So we would do 9x to the fourth, and then that 30x squared in the middle, it would become like two 15x squareds. So plus 15x squared plus 15x squared, and then plus 25. So I didn't change the value, I just like separated the 30 into 15 and 15 because that was the combination that I found that worked. And then now we factor by grouping, so we cut this in half and we factor the GCF out of each half. So from the first half, 9x to the fourth and 15x squared. 9 and 15, the GCF is 3, and then between x to the fourth and x squared, I can factor out an x squared. When I pull that out of 9x to the fourth, it leaves me with x squared, and when I pull it out of, it leaves me with 3x squared. When I pull it out of 9x to the fourth, it leaves me with 3x squared, and when I divide it out of the 15x squared, it leaves me with 5. And then the second half, 15x squared and 25, the GCF would be 5. When I divide that out of the 15x squared, it would leave me with 3x squared, and when I divide that out of the 25, it leaves me with plus 5. Remember, when you're factoring by grouping, you need these two to be the same factors, which they are. So we pulled those out. They group together into one parentheses, 3x squared plus 5. And then the remaining like two pieces become their own binomial factors, so it'd be another 3x squared plus 5. Which if we have two of the same factors, we can just write them as a factor squared, so it'd end up being the same thing. So maybe that was a bad example because that one kind of took a little while too, but just know that like if it's a perfect square trinomial, you can factor it either way. Either way works. So the next section is factor by grouping, which we kind of did on the previous example, but this is just not for a perfect square trinomial, it's just like any general four-term polynomial. So whenever you have like four different terms, and terms are what are separated by like plus or minus, this is one, two, three, four. Factor by grouping is the main way of factoring four terms. I know like with three terms we use factor by grouping a lot too, but there are kind of other options there, whereas here this is the main way. Okay, so step one, it's 5x to the fourth plus 15x cubed plus 10x squared plus 30x. It says step one says to factor out the greatest common factor of all four terms. So for my coefficients, those are like the numbers in front of the variable, 5, 15, 10, and 30. The GCF of those is 5. It's just basically like what can I divide them all by? And get an even number out. So my GCF of those is 5. And then we also have to look at the variables. So this is x to the fourth, x to the third power, x squared, and x. So if they all have an x in common, we can factor out an x. We can factor out the lowest common power that they have. So this last one just has an x to the first power, so that's all we can pull out. So 5x is going to be your GCF. And when you factor out the GCF, it's basically like undistributing something. So like when you distribute, you multiply something in, we're going to be dividing it out. So we're going to divide the 5x out of each term. So 5x to the fourth divided by 5x, we would divide the coefficients, that would become a 1. And then x to the fourth divided by 1x, it would go down to x to the third power. So remember when you are dividing like powers, you subtract the exponents, and this is the x to the first power, so 4 minus 1 would become 3. And then the next term, 15 x to the third power divided by that 5x, you do 15 divided by 5, so 3. And then x to the third power divided by x would go down to x squared. And then the next one, 10x squared divided by 5x, you would do 10 divided by 5, which is 2. X squared divided by x would become x to the first power. And then the last term, 30x divided by 5x, 30 divided by 5 is 6, and x divided by x cancels it out completely. Okay, so we factored out the GCF. This is step one. And then step two says cut the remaining polynomial in half. So by remaining, I mean like what's left over inside the parentheses. So we'll cut just this whole part in half. So that's step two. And then step three is factor out the GCF out of each half. So we'll take this half first, factor the GCF out of there. It's really important that we leave this 5x in front the entire time. So we're going to start to get like into like multiple parentheses. So I'm going to shift to brackets. So the 5x will stay out in front. And then I'm going to pop up a bracket instead of a parentheses there. So from what's highlighted in green, I need to factor out the GCF of those two. So between x to the third power and 3x squared. For the coefficients, the GCF would just be 1 since that's a 1x cubed. And then for the x's, I can pull out the lowest power they have in common, which would be x squared. So my GCF of those two is x squared. When I divide that out of the x cubed, I get x to the first power. And then when I divide that out of the 3x squared, I'm left with just 3 because the x squareds cancel each other out. And you can always double check that you factored the GCF out correctly by just like distributing back in. So like x squared times x is x cubed, x squared times 3 is 3x squared. And then we'll do the same thing, but with the second half of the expression. So like 2x plus 6, the GCF between 2 and 6 is 2 because I can divide them both by 2. And then because the 6 does not have an x, I can't factor out an x. So then I would take my GCF of 2 and divide it out of each term. So 2x divided by 2 is just x, and then 6 divided by 2 would leave me with a plus 3. And then I'm going to close my bracket around here. And then, so this is step 3, was factoring the GCF out. So moving down to step 4, check that the two leftover binomials match. So like what's inside parentheses, those match each other. So x plus 3 and x plus 3, those are good to go. That's step 4. I'm not going to label that because I feel like it's kind of hard to label, but we can move down to step 5. So step 5 is factor the common binomial factor out of each term. So the common binomial factor is that x plus 3. So I can pull out that x plus 3. I'm going to leave this 5x out in front. And then my brackets, I'm going to pull the x plus 3 out. It'll go in parentheses. And then that moves us down to, that was step 5. That moves us down to step 6, group the remaining pieces into their own binomial factors. So the remaining pieces mean like this x squared that was left from the x plus 3 term, and this plus 2 that was left also. So those would go inside parentheses. So it'd be x squared plus 2. And then close parentheses. We really don't need a bracket anymore. I just didn't want us to have like the crazy parentheses over here and stuff. Okay, so I'm going to take that bracket away and then just write the 5x in front of this parentheses. So altogether, it's 5x times x plus 3 times x squared plus 2. And then, sorry, this was step 6. I just wanted it to be easier for us to go back and kind of reflect on what each individual step did. Okay, so moving down to 9.2, we're just doing one problem from 9.2. There's an extra example in the workbook itself, but this one kind of covers both examples, so I feel like this will be sufficient for the video. So 9.2 is solving. We know that like solving by factoring just requires you to factor and then does one extra step. So our equation is solve x to the 4th power minus 16 equals 0. We're going to solve by factoring, and this has two terms. The 16 is a perfect square. Technically, the x to the 4th is a perfect square also. So I'm going to try to approach it with like a difference of squares approach. Sorry for the double approach. Anyways, difference of squares is a squared minus b squared, and that factors into a plus b times a minus b. So I'm going to rewrite my equation with like what quantity is being squared. So x to the 4th is x squared squared, and then minus 16 is minus 4 squared equals 0. And then now I can see, okay, my a is x squared, my b is 4, so I'm going to put it into this formula to factor. So it'll be a plus b, so x squared plus 4, a minus b, so x squared minus 4 equals 0. And then this is why you always want to double check that you can't like factor any further. So now right here, this x squared minus 4 is another difference of squares. We can't factor a sum of squares anymore, so there's nothing we can do with the x squared plus 4, but the x squared minus 4, we can go ahead and factor that further because 4 is just 2 squared. So that means that my a would be x, my b would be 2. I would just copy down the x squared plus 4. So x squared plus 4, and then now this would become like another a plus b, a minus b. So a would be x plus b is 2, a minus b is x minus 2 equals 0, and then now it is factored completely, so we could take each factor and set it equal to 0. So this is one factor, a second factor, and a third factor that all get set to 0, so we should have 3 equations. So x squared plus 4 equals 0, x plus 2 equals 0, x minus 2 equals 0. I'm going to start on the right side, so if we add 2 to both sides, we would get x equals positive 2. Subtract 2 from both sides in the middle, get x equals negative 2. And then for x squared minus or plus 4, we're going to have to solve by square root. So I want to get the x squared by itself. So do minus 4 minus 4. And then I would have x squared equals negative 4. And I'm ready to square root both sides. So if I take the square root of like an equation when I'm solving and stuff, I need to include the positive or negative version. So this would be x equals positive or negative. The square root of 4 is 2. If it's the square root of negative 4, it would be 2i. So we have x equals positive or negative 2i, x equals negative 2, and x equals 2. And then remember when you're solving, like the words like solutions, roots, x-intercepts, zeros, those are all like they all kind of go together in the same family. So if we compare the solutions we got to the graphs now, the real solutions, so x equals negative 2 and x equals 2, those should be our x-intercepts, which they are. there's an x-intercept at -2, there's an x-intercept at +2. That's not to like discredit this solution. It just, because it involves I, it's an imaginary solution, and imaginary solutions don't show up as x-intercepts on the graph. So you should only have real like number or real solutions as the x-intercepts, but the 2i is still like a valid solution essentially. Okay, so the last thing, this is like really quick. If you want to see another example on like this type of problem, it's in 9.2. I just wanted to keep the video, I know it's not short, but relatively short for you guys. Anyways, the other example starts off from factored form. So it starts off right here where you just kind of set each factor equal to 0. So it's a quick one to look at if you're